first of all, this is way more people than I was expecting, so thank you so much for coming. I was actually just expecting GAN and my supervisors, so this is amazing. Shows people are interested in VAEs, I guess, so that's cool. My name's Matt. I'm a PhD student with Rich. I'm also a lecturer at the IOSR over the other way, the sound recording place. But audio was getting a little bit stale for me, so I wanted to do some vision. Yeah, so we're doing vision, but variational autoencoders. So I'm going to talk around the topic as well. It turns out generative models, there's a lot of overlapping theory with information theory. We're going to cover a little bit on GANs as well, but just briefly sort of tying things together. And a little bit, well, I kind of find it fun, the causal inference kind of perspective, which is getting more important in ML now. Add me on Twitter, if nothing else, if you don't get anything from this. I'd like some Twitter followers, is that right? And also, as part of this work, I collated 300 papers on VAEs over the last few years, research over the last few years. And I've read most of them, and I've tried to sort of build in the research into this presentation. But it's also, hopefully, a useful resource for anyone doing work with VAEs, because if you're searching for literature, sometimes it can be a bit of a faff. So maybe this is an opportunity to get it all in one place. With that said, I'm going to do some boilerplate. Is that me? That's sound effects and everything. All right, so I just wanted to put this slide on here to make sure that if you have no idea what I'm talking about, this is your excuse to leave. You won't be judged too much. So if none of this makes any sense to you, then you can leave, and that's fine, no worries, because obviously it's a lot of your time if none of this makes any sense. So VAEs, this is just the sort of a sort of silhouette of a VAE, what you might be familiar with. Also for autoencoders as well, the idea is we shrink an image down into some sort of compact representation, and then we decode it again to recover the original image. So hopefully that's got some familiarity, maybe rings a couple of bells. VAEs are used for lots of different things, so they're a really flexible model. We use them for generating images and manipulating images, so I made one that allowed me to puppet Donald Trump's face, which was quite fun. So I could look into a camera and move my mouth, and I made Donald Trump's mouth move. So you can do cool stuff like that, or you can do more serious things like use it for downstream tasks, object detection, object tracking, all that sort of important stuff. Change detection, debiasing, denoising, and also compression, which might seem kind of intuitive because we're shrinking information down to some representation and expanding it again. And then there's all the other applications you can think of. Whenever you've got a useful representation full of information, so whatever that might be useful for. These words I wanted to sort of run by you because I'll be probably using some of them interchangeably, but also I want them to be reasonably familiar before I start. So these last three I'll start with: causal factors, generative factors, and latent factors. The idea is, in this representation, they're not quite the same thing, but I'm going to use them somewhat interchangeably in this context. These are the factors that are responsible for generating our data. So we have our observations, and obviously behind that, we're assuming that there's some sort of data generating process that's responsible. So we're trying to learn those in here. So causal factors, what caused our observations; generative, what generated our factors; and latent, they're unobserved. We don't have data for them explicitly. We've got to try and infer them using variational inference. The last three, the top four rather. So embedding and representation, I'm going to use those somewhat interchangeably. What I mean is something that, a representation of some higher dimensional space. We have a high dimensional space, like image space. We want to represent all the information that's in that space. We're going to be representing it with a representation, which is also an embedding. So we're embedding that information into a compact space. Manifold and subspace. I imagine many of you have sort of been exposed to PCA before. That would be like learning a linear manifold. So we're trying to identify the sort of subspace, the few dimensions that are really sort of containing all the information that's in our data. And as we'll come to see, images are very redundant beasts, and actually we can represent all the information in an image in quite a compact subspace. So yeah, you can leave now if any of that is just complete garbage and doesn't make any sense whatsoever. And as I said, no judgment. All right, if we're all still here, that's amazing. Don't be scared by this. This is again boilerplate. What I've found is when I'm navigating the research, there's a lot of very dense mathematics for variational inference. There's a lot of rich statistical heritage, and it was actually quite difficult. Every time I get a new paper out, I'm sort of having to work my way through this maths. But what I would encourage you to do, if you do come back to this, then these concepts are really useful. Grab my presentation slides. because it ends up not being a task of, oh, what's the sum overall of x, of p of x log p of x. Ooh. It's actually, oh, that's just entropy, that's the information content. So it becomes more a case of sort of recognizing these symbols and these phrases of equations that you can just sort of easily sort of skim through and recognize them. So I put a bit of time into doing that just to speed up my workflow, and actually paid dividends, not literally. But yeah, so mutual information, a really important concept in all of deep learning, but especially for the theory behind VAEs. Divergences are really important, as we'll come to see in other ways of sort of measuring the differences between distributions. And then things like total correlation as well. We'll sort of come back to them, but as I said, this is more like a boilerplate slide, just to, if you come back to it, these are useful things to be familiar with. And the final thing for the boilerplate is, again, I mentioned these briefly on the previous slide, F divergences, total variation, IPMs. So these will take this form, and all they are is a way of measuring the difference between between distributions. So what you'll find, if anyone doing deep learning, machine learning, becomes a task of density estimation or conditional density estimation. That's what you're trying to achieve. Anyone who's done that is doing density estimation. And these are some ways to measure how far off we are from achieving a good density estimate. Anyone that's done GANs will probably be familiar with Jensen-Shannon divergence. More recently, Wasserstein and MMD come up a lot. VAEs will see the Kullback-Leibler divergence a lot. And we'll also sort of briefly mention how any maximum likelihood learning is just minimizing Kullback-Leibler divergence as well. So these are like quite fundamental topics that are relevant for just about everything we're doing in this department, I would imagine. Right, so that's the boilerplate out of the way. We're going to have breaks every hour. And I'll try to keep my eye on my phone if I forget and just shout up. I don't want to get to the end and just be looking at a can of dead mackerel eyes. So yeah, break every hour. Any questions throughout, I'd suggest you ask. Probably forget by the end otherwise. So just jump in whenever you want. Make sure you're like not sort of getting lost, and then it sort of becomes a waste of time for you. Everyone all right with that? Cool. All right, so this is what I'm going to try and get through today. Again, if we don't get to the end of it, I'd rather you get more out of it than us finish it, so to speak. Firstly, motivation and context. I'm going to put VAEs in the landscape of other methods. So there's lots of other methods we can use for density estimation. VAEs are just one of them. I'm going to try and sort of place them in the context of that. Now I'm going to talk about just at a top level what the VAE architecture looks like, a bit like that silhouette we saw. But what we'll find is, I guess, there's some aspects of VAEs that aren't necessarily obviously intuitive from the get-go. And so if anyone's looking at VAEs on GitHub and downloading some code, you might actually find it hard to know what that code's actually doing. So you see these sort of functions and so on, but you might be like, oh, I don't know what the KL divergence is doing there, what's that for, what's prior regularization, I don't know what these things are. They're in the code, but I don't know how they're becoming useful. So after we've done that sort of top level VAE architecture, I'm going to go through the objective function, I'm going to derive it with you, and then we'll go back to the architecture and sort of embellish it a bit more so we understand where these things come from. And then I'm hoping that if you come to the GitHub, sort of repos and so on, it'll be straightforward. Like, oh, that's that KL divergence, Matt talked about that, we actually derived it together, etc., and we know what it's for. Once I've done that, I'm going to talk about open issues with VAEs, what's the sort of hot topics, and then I'm going to do the causal interpretation, and talk about evaluation. It's a really important thing. I think it's all too easy just to rely on, say, accuracy scores or whatever you're sort of used to using one metric to sort of validate a model, especially with VAEs and sort of unsupervised methods and GANs. It's really important to look at these models from lots of different perspectives, because, you know, like for a GAN, you might generate an image and you say, oh, that looks great, it's done. But actually you find that there's a lot more to it than that, and you might be doing yourself a disservice by not looking at it from more angles. And then I'll finish off with some state-of-the-art, just briefly, in what we want to do next with VAE research. Oof. So, I'm going to try not to get too much dry biscuit mouth. So, the revolution will not be supervised. A bit of a sort of a fun, memey kind of thing that Alexei Efros actually came out, John Colonos pointed out to me, actually came out in 2017. This was a play on the revolution will not be televised, which I think was a sort of civil rights movement. So it's a bit of a sort of fun thing, but it does have a serious message, which is that we can't rely on supervised data sets for the rest of our lives. They're expensive to collect. Humans don't use supervision, actually very, very little at the time we use supervision. So if we can leverage unsupervised learning, or even self-supervised tasks, or weakly supervised, semi-supervised, then we're actually sort of achieving models that achieve a bit more intelligence than just the straightforward sort of curve fitting. So the models I'm going to talk about are unsupervised models. They don't have to be, you can incorporate supervision. But again, the advantage of unsupervised models is we just have some data. We don't need labels for it. We can collect it from the wild. It's easily accessible. And if we can learn from that, then that's obviously far more advantageous. So as I mentioned, all of the stuff we're doing is density estimation. And if we know a bit about density estimation, I'm just going to go through just some, I guess, fundamentally stuff for density estimation first. Let's say we have two-dimensional data. This is a smattering of data points in that two-dimensional space, and we might initialize, say, a Gaussian, might be isotropic to begin with, just here in this space, and we can see that it's a really poor fit to the model. So we've got this density that exists, and we've got our sort of our model density here. And if we were to calculate the likelihood of any of these data points given that model, they'd all be very, very low, right? So all of these points fall on the tail of that Gaussian, and we're going to get what's known as a low or poor likelihood for that model. Now, if you're in Mark Plumley's class, you might be able to do some linear algebra, fiddle about with some Gaussian equations, and then just calculate your new mean, your new covariance, and you'll get to where you want to go. That's great. If you're using some kind of updated or iterative approach, then you might sort of move this iteratively until you get your maximum likelihood estimate. So Fisher gave us maximum likelihood, which is a great tool. It's not the only thing we use, but it's very useful. It's seen in most of our applications. So the idea is we're maximizing this value, and this value is just the probability of all these data points under the model that we're proposing. And if we sum that all up, we get some likelihood estimate. We're trying to maximize that by adjusting the model parameters theta. Now it turns out with just a few lines of maths, and it doesn't take long, you can show that maximum likelihood estimate is the same as minimizing the Kullback-Leibler divergence. This is the equation for Kullback-Leibler divergence. There's a few different forms that you can sort of relate, and again, this is what I'm talking about, recognizing that as a symbol for KL, and you can say, oh, it's KL, I don't have to, oh, I wonder what expectation over X, and so on. So we're minimizing the Kullback-Leibler divergence, we're minimizing the difference between two densities, and then the density of our actual data. So this is just one instance where this KL sort of pops its head up, and we'll start to see that it sort of comes up quite frequently. So we actually have loads of methods for doing density estimation already. Before deep learning came around, these are the sort of traditional techniques, and they fall into two main camps, direct methods and indirect methods. These are also called explicit and implicit methods. And these two VAEs fall into this variational inference group, a sort of more modern version of it. But we might be familiar with some of these other ones, like we've got map estimation here and maximum likelihood estimation. We've got some Monte Carlo over here. We've got expectation maximization. They're the ones that I was most familiar with. And then on the other side, we've got, say, two-sample comparison. That's the same as a GAN. GAN is doing a two-sample comparison or density ratio estimation. And then there's other ones that we might have sort of heard about, like MMD and maximum mean discrepancy. So these two camps, the reason why they exist is because in this area, we can actually calculate at least a proxy for how well our density is doing at matching our density that we want to estimate. So we can literally get a calculation that's a fairly close approximation, if not the correct estimation of the likelihood of our data under the model. The trouble with this one is we're using, at best, a proxy. So two-sample comparison with a GAN, it's like, well, I've got this sample which comes from my generator. Is it from the same distribution as my real images? All you can say is yes or no. Right? So if you were to produce the same image again and again and again, you just keep saying yes, 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 all the same. So you get sort of a false impression that your GAN's doing a good job in matching your densities, but actually you've just done what's called mode dropping or mode collapse, are slightly different things. And so you don't have a direct way of measuring the success of your GAN at approximating that density. So, excuse me, what we'll see is that, these are slightly, you have to go around sort of corners a little bit to get where you want to go with the indirect methods. But again, these are actually all methods that are traditional. These exist already. So you might be asking, well, if we've got all these methods, then why do we need deep learning? Where does deep learning fit in all this? There's quite a sort of abrupt quote by Zhao. He said, unbiased and consistent density estimation is known to be impossible. So it's actually quite a difficult task. We might be in like 2 dimensions and have a Gaussian. We might be doing that in Mark Plumley's linear algebra class, but actually when we're dealing with these high dimensional data, especially in this department, we're actually going to be faced with a really difficult challenge. So just to sort of, I guess maybe I'll make that a bit more intuitive. This is just some randomly sort of perturbed images. These are just randomly assigned pixel values, just 4 of them, just a random sample of 4. And you could imagine that if I carried on producing these image samples, I'd come up with, like, say, 10 million of them. Do you think there's a chance that any of them would resemble my face or a name in text? Right? How many of these random perturbations would we have to make until we somehow stumbled upon a realistic looking image? It's like astronomically small. So I mean, worse than that. So for MNIST, we need a histogram. Well, there's 10 to the power 236 possible combinations. So actually, the number of molecules in the universe is much less than that. I think it's like 10 to the 86 or 10 to the 72, somewhere around there. But anyway, we're a long way beyond this. All right, so this is actually a good thing and a bad thing. The good thing is that the natural images that we're concerned with actually occupy a very, very small space in this huge space of possible images. So that's when it comes down to manifold learning, which is that term I used before, manifold. We're trying to find the manifold of natural images in this very, very high, sparse density. And we're certainly not going to be able to use a histogram. So imagine every possible image counts as a count on a histogram. We've probably got loads of data sets, and only one image would only ever end up in one bin. So the rest of them will be empty. So we're actually faced with what seems like an impossible task. But again, the sort of flip side to that is that, it says here, real-world data presented in high-dimensional spaces are expected to concentrate in the vicinity of a manifold of much lower dimensionality embedded in this high-dimensional space. So this was an image that I sort of recreated. It's just obviously not the most pretty image. I'm not trying to get credit for my skills there, but this is actually from a noise reduction paper. So the idea was in this that if you learnt the manifold, any deviation from that manifold is probably due to pixel noise. So by removing the noise, we're actually projecting the image back into the manifold. And so when we do see deviation from that manifold, a lot of the time it's actually just due to random noise. So again, if we can learn this manifold, we're in a really strong position. So one possible way to do this is to start representing our images in a compact space. So this is our space of images, 10,000 dimensions for 100 by 100 image. These might be images of butterflies, and this cloud is supposed to represent the fact that they're sort of clustered in a certain area in this very high dimensional image space. And if we can learn this cloud, then that's great. We're basically identifying how to move around in this density that corresponds with images of butterflies. And one way to do that is to actually sort of map this into a low dimensional space. Now, that space doesn't have to be meaningful from the outset. You could imagine this is actually a lookup table, like a byte address. In which case, every time I map it there, I'm sort of saying, well, this is where it's stored in memory. And that would mean you could always map from the same image to the latent space, not the latent space in this case, the lookup sort of address table, and then back again. And you'd always get perfect reconstructions, perfect samples. If you sample from this, you pull out a lookup address and you go, oh. Sort of information that's relevant. There's a mutual information between the image and that space at that point. So what would be nicer is, instead of achieving a lookup table behavior, which is actually one of the sort of criticisms of deep learning, is deep learning is just complex lookup tables. I want to do something a little bit more than that, and not just learn a lookup table, but learn a density in here, a density over latent factors, a density over the manifold that we're trying to learn in here, so that we have like actual semantic information. And then we can actually move around in here. We're not in a lookup table. We can actually interpolate as small grain as we want across that density, and in so doing, we'll see corresponding perturbations in the image here. So it might be that one of these dimensions in this latent space corresponds with butterfly color, and then we can literally tweak that and change the color of the butterfly without changing anything else. So this is our task for mathematicians. I decided to include these, injective, surjective, and bijective. It would be nice maybe to have a bijective mapping. In reality, we might lose some information, so it's maybe not perfect bijective mapping, but we'll come back to some of where you end up on this, depending on how you optimize. So I'm going to set out some goals then for density estimation, and specifically in this sort of scenario where we're mapping it to a low dimensional space. First one, it'd be nice to achieve faithful reconstruction of the input sample. So if I start off in this space with an image of a butterfly I've captured in the real world, I map it into this space. If I was to then reconstruct it, I get exactly back to where I started. That'd be great. That's different from high sample quality, which is what a GAN achieves. There's no encoding in a GAN, you're just generating an image of sort of a random seed. So in a GAN, and we can still achieve this in this scenario, we just sample from in here, and then we end up with a new image that we've never seen before. But that image needs to look realistic, it needs to have high quality. So it needs a high likelihood, in other words. We want to achieve rich representations, so again this needs to be informative, and then we can use it for downstream tasks. So if you're doing reinforcement learning, for instance, you might have some sensors looking around, that's high dimensional data, you might want to embed that in a nice compact representation that contains all the information you need, and then you can use that for any other downstream task part of your RL agent. We want to approximate the data distribution. This is a whole density estimation thing. Again, we're not just estimating the density of the latent factors, we're also estimating this density here. So we can match the density. If we were to sample from this, we'd get that density back. And that's one of the things, again, with GANs, like you might struggle to sort of recreate the whole density. In fact, this is a struggle with all models. But also this latent space, so it'd be nice if we learn the real generative factors. We actually get some semantic information and learn what's actually generating our images. So with faces, for instance, we might get dimensions out that correspond with whether or not someone's smiling, what's their head pose, and so on. And it would also be nice if these factors are disentangled, so that I have a nice independent control over those generative factors. Again, we might also want to remove nuisance factors. This could just include noise, or it could include other things that you specify. You might want to say, I want to remove head pose, so that every time I get an image in, I actually project it to some sort of canonical representation and remove the head pose, and I always get a frontal version out of the head. That would be cool. And then finally, well, not finally, on this slide at least, compression. This is obviously compression task. If we map it like this, we're compressing all that information and we get back. So what we'll see is VAEs are actually being used more and more now for achieving compression in very successfully as well. So a couple of other things that would be nice to achieve. These are icing on the cake. If we show our model images of cards with 3 points on, we might want to generalize that so that when we sample from it, we can also generate 4 points and 2 points as well. So rather than just learning the single mode of the distribution we show it, it'd be nice if it actually generalizes and gets a little bit more applicable, more widely applicable, probably going to help us when we actually deploy the model. Similarly over here, same example, we train it on red squares, red balls, and yellow balls, and then we might want to be able to generate, say, yellow squares or cubes. And finally, we might want to do some interpolation. So again, if we're learning actually a manifold and we're learning a density properly, we're not just using straightforward lookup tables. Right? So again, one of the major criticisms of deep learning is, pass it through a CNN, it's just doing sort of patchwork sort of lookup table. But actually, if we're learning a density, I feel like we're doing something a bit more than just a lookup table. We're learning a density that we can move around in. So each of these columns is a dimension in that latent space, that compact space. This was trained on faces, obviously. To put my face in, so that's me, you might recognize the glasses, and then we can move around up or down and perturb the values of those latent factors and then generate the image. So in this dimension here, you sort of made me more handsome and more sort of grizzly. This one here makes me look a little bit like Donald Trump, maybe. That's great, always want a latent space to do that for me. Over here it sort of makes me more look like a supermodel, but of a different gender. And over here we've got me looking like Lou Reed, so it's ideal. But anyway, the point is that we can move around in a semantically meaningful way, not just like, if we were learning a lookup table, as soon as we perturb that space, we'd actually end up in an area of zero probability, so we get garbage out. Right? But this is learning a density that we can actually smoothly traverse. So they're the goals that I want to present you with. This would be ace if we could do all of them. We'll find that some models can do some of them, some models do 1 or 2 of them really well. VAEs end up doing all of them somewhat well, but we'll see how that sort of pans out. So as I said, we can't just use a bit of linear algebra to solve our density estimation, especially not with the dimensionality of the data we're dealing with. So we're going to use some sort of density approximation schemes, and again, we either have deterministic methods where we can, like Gaussian mixture models or mean field approximation, where we can maybe get some kind of analytical solution out. But otherwise, we're stuck with these sampling methods, MCMC, Gibbs sampling, Hamiltonian Monte Carlo, or end up with some kind of black box method, and VAE is one of these. So the trouble with these is they will take too long. Like sampling Monte Carlo, it's very computationally expensive. It's going to be a bit of a pain to implement that. So what we'll see is that VAE is actually a sort of an updated version of variational inference that we can use to learn densities much more efficiently in high dimensions. So these models that we have access to, these deep learning models, these are the 4 most common for sort of unsupervised generative density estimation models. So this is GANs, probably heard of them. Autoregressive models, they generate pixel by pixel So they generate a pixel and then they condition it on the previous pixel or pixels. Flow-based models, they start off in a high-dimensional space with a very tractable distribution like a Gaussian, and they apply a series of invertible and differentiable transforms until we get to the density we want. And then there's deep latent variable models. There's lots of different names for these things: variational inference, black box, amortized variational inference. But this is where VAEs lie, because we're trying to learn the latent factors responsible for generating our data. So, all unsupervised, but they again fall into these two camps, explicit and implicit. Explicit, we can actually measure how well our model's doing. Is it any good? We can actually get a proxy for that fairly straightforwardly. But then there's implicit density models, which are GANs, which need a little bit more sort of fiddling with in order to actually estimate how well our model's doing. But what I will argue that regardless of which one of these you choose, you do need to evaluate these from multiple different perspectives, especially depending on your goal. It's quite goal dependent. So, what if we pick an autoregressive model? The trouble with this, we're conditioning every pixel and every previous pixel is very slow to sample, take a long time, and they also don't give you any single representation layer. So if you just use an autoregressive model on its own, you don't get that nice compact embedding. You can combine this with a deep latent variable model as well, but just on their own, they don't give us that nice compact latent space that would be great to use for downstream tasks. Similarly with flow-based models, we again don't have this embedding. We don't achieve that. Flow-based models, we start with a high-dimensional space, same dimensionality as our data, and we apply the transforms until we get to the density we want. You can move backwards as well, so you can encode and then decode, sort of sample and also reconstruct. But it's slow to encode and then decode because you've got to move in both directions. But again, the main thing is you don't get this embedding here. Finally, stay tuned for these, jack of all trades. VAEs don't just have to be jack of all trades, you actually tune them for specific tasks to become very good at what they do. So I guess I'm a bit of an advocate for these. GANs, they're really fun, but they're slightly less principled at the moment because the maths is sort of catching up, the theory's catching up with them. At the moment they're very difficult to train, there's a lot of oscillation in that sort of adversarial game that you end up playing. And also sample diversity is the big thing. I know someone who was actually doing some work here, I can't remember his name, but he was actually using a GAN to generate data. And I would strongly advise against that. Again, with GANs, it's hard to estimate how well your density is actually matching the true density. And if you're just sampling images and you're like, oh, these look great, these look really realistic, it's like, okay, but have you seen an image that doesn't look like every other image? How do you measure that diversity? So very difficult to even do subjectively, let alone objectively. So what we'll find with GANs is that they tend to collapse onto a single mode or a few modes, and you end up only covering a small region of your density. So that's a big issue with GANs. Don't use them to generate data just yet, at least not if you want that data to be fully representative of your population and your real data. But you do get amazing samples out. But one of the things that people maybe not quite so aware of is that actually VAEs can achieve equivalent reconstruction quality as well, so it's just as realistic. So in that sense, well, at the moment at least I'll probably pick a VAE, easier to train, more variational inference heritage behind them, and they get similar results in terms of quality to GAN and more diverse images as well. This is just a brief slide just to show you what I'm talking about. If my data look like that, and I want to approximate this with some distribution, maybe I've got some prior expectation, and I use KL divergence, that's that maximum likelihood estimate, I might get some result that looks a bit like this. It's a little bit like an average between the two. But it's called zero avoiding behavior. It tries to assign probability to the whole space. So even here you get some probability, even though it's sort of clustering the probability around here. MMD, on the other hand, which is an IPM, integral probability metric, tends to cluster it a lot more closely on one of the modes. And then Jensen-Shannon divergence, which is the GAN vanilla objective, is even more aggressive. So again, you're trying to cover all this data, you use a GAN, and then boom, you've only got one mode in your data. So that'd be a case of mode dropping. And that actually brings me to the end of the motivation and context. I wanted to put VAEs in the context of all the other models. So I hope maybe that gives you some idea of where they sit with regards to the other options. So the next thing that I want to do, unless there's any questions that anyone wants to jump in with. All right. VAE architecture. This is quite top level. This is similar to the thing we saw before. And the idea is we have a distribution of images, P of X, this is our real data, and we're going to encode this into this bottleneck layer, We're going to have some of these distributions to represent what we're encoding here, which we'll come back to in more detail. And then we're going to decode that and recover this conditional likelihood here. This is a conditional distribution, x given z. We're going to call z our latent factors. Z is the sort of compact representation of learning in this layer here. So you can write that as encoding encoding x for z, and then decoding z gives us this x hat, this sort of reconstructed version. Now, one thing I'd recommend people get familiar with, if they're not already, is probabilistic graphical models. These are great for communicating a lot of information in a very, very small space. So this is actually the VAE. And we haven't actually drawn the VAE yet in full. So you can see that actually this does everything you need to know, not in terms of architecture, but in terms of what your world model is, what you're actually modeling the data with. So this is saying that I have my data x, and I've got each example is I, and I have this plate notation that says that's repeated, this graph is repeated 1 to n times, n is the size of my data set. And what I'm doing is, I'm doing inference, which is this dotted line, to infer this unobserved variable, z, that's our latent factors. Here, that's why it's not shaded in grey. And I'm also using that to generate x, so there's that solid arrow moving down. Now with deep learning, we have one set of weights and biases, generally. So these are outside the model, they're not inside the plate. With old variational inference techniques, we actually have parameters for every single data instance. So this is why VAEs are sometimes called amortized variational inference techniques, because we're amortizing the learning for the whole data set over these single sets of parameters. So this parameter phi, these sets of parameters phi is responsible for inferring the latent space, and this set theta is responsible for generation. And so we only get one set, but the idea is we're universal function approximators with deep learning. So even though we've only got one set, that's all we need. We can do whatever we want. It's all at power at our fingertips. So that's the top level. Now I'm going to talk about the objective. It's a little bit dry, but I think it's important for understanding where these terms come from, and when you use VAEs yourself, when you get that GitHub code that you're ripping off someone, then you can understand what that code is actually doing, and you can manipulate it yourself in an intelligent way. So garbage in, garbage out. Your choice of objective really defines what you end up learning. And so, some of these tweaks might seem subtle, but they actually have quite a large impact a lot of the time. So if you're choosing your divergence, whether using KL divergence and IPM, these things are going to affect how you approximate and either mode collapse or get nice coverage over your data, etc. So actually, this is quite an important consideration anyway. And just, I guess, take a deep breath. So this is what we start with at the top here. This is actually maximum likelihood. So here we want to achieve our likelihood. This is a log likelihood, p theta of x. This is the likelihood of our data under the model. And over here, we've just used a bit of simple probability to express it in terms of its latent factors as well. That's all it is. Any mathematicians, by the way, is probably very sloppy, so don't get too angry with me. I think algebraically it will still make sense, and all the steps are there. More than anything, it's just I hate fiddling about LaTeX. So maybe I've dropped a few little subscripts here and there. But anyway, this is correct. So the first thing we're going to do is use something called the identity trick, which is very useful for manipulating these equations that include densities and distributions. So the first thing we're actually going to do is just multiply and divide by q phi z given x. So what this is actually what's known as the approximating distribution. We don't have access to the true posterior distribution. This is a Bayesian kind of approach. We don't have access to the true posterior here, so we're going to use q, which represents an approximation to that distribution. We're going to multiply and divide by it here, so we haven't really done anything. And what we're going to try and do, essentially, this whole task is just about writing this in terms of things we can actually compute. Because when we're stuck up here, we don't have access to these things explicitly. We can't compute, we can't integrate over all possible latent variables. For a start, we don't have the latent variables yet. We have a prior for the latent variables, p of z, but we need to try and write this in terms of stuff we can actually achieve computationally. So once I've multiplied by and divided by q of z given x, the approximating posterior, I can now take an expectation using that. It's literally the same thing. If you've got this in an integral, you can rewrite that as an expectation. So now I take an expectation where we're sampling z from this approximating distribution q of z given x. So an expectation is just where we're going to compute almost like the average by sampling from that distribution. So as soon as we start to see that, you might think, oh, maybe I can do a Monte Carlo approximation to this. Maybe I can start sampling So this is essentially the same thing from here to here. All that's happened is that this one has disappeared because we're building into the expectation, and that's where the integral sign disappears. What we're going to do now is something called Jensen's inequality. We can apply Jensen's inequality, which is for a convex function, it's saying the expectation of a convex function is always less than the function itself. So we have a nice curve. We take 2 points. We want the expectation. It's always going to be below. So we take an expectation here. We can actually move the log here inside the expectation. So it might seem I'm sure Jensen wouldn't feel like that, but at least for this step it's fairly trivial. But here we end up with now what's called a lower bound on that likelihood that we're trying to approximate. We're trying to get this at the end of the day, but we end up with this. So again, Jensen's inequality, we've got a curve, take an expectation, we end up somewhere below it. So whatever we're computing now is below that. That's why this ends up being called the evidence lower bound. We've got an inequality there. We're trying to push it as high as possible to get as close as we can to the true log likelihood, but we've only got a lower bound at the moment. And this, if you rewrite this in terms of KL divergence, you've got this fractional here and an expectation. You can write this as follows. So take the expectation over our samples from that latent space, our Q, our approximating distribution for the posterior. Where am I? Here we are. And we're going to compute the conditional likelihood from that. So this is essentially, when I sample from my Z and I reconstruct an image, how good is that image? This is literally just a reconstruction term. So you can substitute in there mean squared error. If your Bernoulli distribution, you can substitute in there cross entropy. So you're sort of starting to talk about real loss functions now that you can implement in, say, TensorFlow, or, you know, I don't know if there are any other libraries, but TensorFlow. And then over here we've got the KL divergence, and this describes the difference between your approximating distribution and your prior. This is your approximating posterior. So this is what we're learning in that latent space, and we're basically putting a penalty on it. We're saying, well, how different is it from our prior expectation? So this is where the Bayesian thing comes in. You have to specify yourself what you think this prior is going to be. Is it a Gaussian? If so, how similar is my latent space to a Gaussian? If it's not similar, we're going to penalize it. We're going to make it like a Gaussian. And you can just rewrite this, just expanding that KL term here. But fundamentally, this is the equation you're going to see all the time. So this last one here says the log likelihood, basically how good your model is at approximating this density, is represented by this lower bound. We're not going to get exactly there. We get as close as we can, ideally. Reconstruction error, penalized by how different our latents are from the prior. So here we can get rid of this by having a really nice decoder that says, oh, it's going to generate a really nice looking image for us. So a nice deep transpose convolution network here. And then over here we're penalizing it if from what that's derived from, the latent space, is too different from our prior expectations, which we can define. All right, now there's other ways to write it as well. But what I wanted to do one more is just to try and explain what actually makes up the difference between our lower bound and our true log likelihood here. So I'm not going to step through this. It's a more complex derivation. I put 3 up there because if you're doing this yourself, there's lots of different avenues you can go down to try and get to where you want to go, and you'll get different results. And so you can tweak things and hone in on what you want to actually improve or not. So if we actually do it this way around, we end up, I think it might be on the next slide. We actually end up, where is it? We end up here. Where is it? This one. Okay, so here's our log likelihood, log p of x here. And on the right-hand side, we actually got what we had before, which is exactly the same as what was on the previous slide that I went through, so don't worry about that. But then on this side here, we've got this term. This is the KL between your approximating distribution and the true posterior. So this is actually what makes up the difference between your elbow, your evidence lower bound, and your true log likelihood. It's this divergence between the approximating distribution that you chose and the true. So this makes sense, this makes intuitive sense. So we're going to choose an approximating distribution. We might choose some Gaussian distribution, and we might choose a Gaussian for the prior as well. But if our Gaussian is unable to actually model the shape of our latents as they are in that latent space, then we're never going to get where we want to go. Like, we can only manipulate Gaussian so much, we've got so much control over its parameters, right? It's always going to look like a Gaussian at the end of the day. So what made up our elbow, what the difference between where we wanted to get to and where we were with the elbow, is this term here, and this is really dependent on what you choose for your approximating distribution. So these derivations I think are useful because you can identify and justify for your own publications why you choose a particular variational distribution, because you can say, oh, well look, this is a problem here because my latent's expected to be distributed in some weird way. Can't use a Gaussian for that, so I'm going to say use a flow model or something else to approximate that true posterior distribution. So what I'm going to do now is return to the architecture via this. So this actually describes what I was kind of talking about before, that mapping. We have our data distribution here, these are our images, and we've identified that manifold, and we're going to map that into a latent space here, and then we're going to reconstruct it. So if you use an autoencoder, which some of you might be familiar with already, without the variational bit, then this is the sort of behavior you get. Let's say we have a prior that's kind of like a cross shape, it's just arbitrary. What you end up getting is gaps in between each of the latents that you've mapped the image to, and also gaps here. You get perfect reconstruction. This point should end up where it started. So with autoencoder, you end up back where you started. But this is subject to things like overfitting, because you use a training set and you train on a training set, you might get great results, but as soon as you show it some new data, where does it map a new data, unseen data point to? It doesn't really know. It's got no way of learning a mapping that it hasn't seen before. So the whole, one of the main advantages of variational inference and VAEs is that if we're learning a distribution here, we can actually keep some continuity, keep a smooth density in that latent space, so that when we map an image to it here, it doesn't matter if I sort of move a bit off here when I go to my test phase, I'm still going to map it back to somewhere in this, and it's still going to be a realistic image. So we're effectively adding a bit of noise to it in order that we can move around in that space. So this is an ideal scenario here. If you remember before, we had that KL term here. This was the thing that penalized it to be like the prior. If we set this to 0, or even if we achieve this and we get perfect like the prior, then we should end up somewhere here. So this would mean that we've approximated the prior exactly. We've basically removed all the information from our images. We're mapping it to a mean 0, covariance, diagonal covariance, Gaussian, and the whole thing's a mush. Right? We're just adding noise, we're flooding it with noise essentially. If we remove that term entirely and we let it do autoencoding, then we end up here. So we map each individual image to a unique position in the latent space and then back to a unique reconstruction. But then somewhere in the middle, which would be nice, we end up here. We add a bit of noise to it, there's a bit of sort of like jitter there in the latent space, but then I can sort of move around in these spaces and I can interpolate between these images. So you might have seen like style transfer stuff in papers, where you can start off with one image and try and move to another, and if you can achieve a smooth interpolation between them, you might be doing that by moving smoothly through this space, which you can't do in the autoencoding domain because these are all 0 probability of occurrence. But here you can start to interpolate between images. Here you end up getting, I guess, would be mode collapse, because you're collapsing all of the data points onto almost a single point in the latent space, and then all of these get recovered into approximately the same point in the reconstruction as well. So setting that beta parameter has a bigger impact on where you end up, but also what distribution you choose will affect what behavior you go for. And again, if you're using an autoencoder, you're probably going to end up here, and you have to be really careful about overfitting to your data with that. So the good thing about VAEs is actually quite hard to overfit, unless you remove that term. Everyone good? Ish? Yeah.
The lower line here, is it when beta is infinite or when beta is 0?
This is when beta is infinite. So we've pushed it so much towards the prior that that we've basically just got mean 0 covariance Gaussian there. Here we're basically removing the term entirely, and we're just relying on the log likelihood, the conditional log likelihood.
So if we had a perfect prior, it would not blur the data, it would just represent it, right? This is only because we have not ideal prior, right?
Yeah, I suppose, yeah, if you already know what the latents are going to look like, you're in a great position. I guess in reality we're never going to be quite like that, and even if we're almost like that, we still have to bear in mind how much we push it towards it and how much we're trading off that reconstruction accuracy. Because the one other thing to, I guess, bear in mind is that what's your goal? Is your goal nice quality images, or is it encoding some really informative latent space? And actually, as we'll come to see, if we're not worried about reconstruction, you actually get more information in the latent space. So yeah, there's some trade-offs to be sort of played off against each other. So this is also a little bit like filtering, linear filtering. Essentially, you could see it sort of convolving the input image with some noise, really convolving the latent space with some noise. Imagine if this was our training distribution, the proportion of red color sort of dots in an image that the network saw during training. Say there was either 0.3 or 0.4. When I add this Gaussian noise, essentially, if I'm putting a prior on it, I actually end up here with the VAE, depending on how narrow or how much we push it towards that prior. So this is predicted by convolution. You could get the same result if you just widen the variance of your filter. These would be the same. And then here is a different scenario where the proportions are slightly further apart in the training distribution, and here you obviously get nice separation. So this paper was just showing that VAEs are essentially doing linear filtering in this latent space, and in so doing they're almost effectively convolving something with a bit of Gaussian noise, and how much you convolve it with that noise is kind of set by that beta parameter, and the variance of that Gaussian is set by your variance of your prior distribution. There was this paper that went through the details, really nitty-gritty. It decomposed the elbow into all of its constituent terms, gave them names, went through the effects. So if you are interested in this sort of aspect of VAEs, I strongly suggest you check out this paper. By the way, my referencing in this slideshow is quite brief because there's a lot of them, but they're all in that list. So if you search the name that I've put up here and in the list and the date, you'll pull up the reference itself. So this goes on, and it also breaks down all the previous versions of VAEs into what terms they're actually using for their objective. So actually this is quite a hot topic in VAEs. What objective do I use to train them? And they are quite young in the sense, I think Kingma came out with them in 2014, so they're fairly young, and they haven't had the same attention as GANs have, despite the fact there's actually a lot of variational inference or theory behind them. So yeah, there's opportunity there for more work. All right, so now I'm going to return to, one more thing. Okay, so the big thing that prevented us from using VAEs before, using variational inference in deep learning, was the fact that we can't actually differentiate, backpropagate in like deep learning library, like TensorFlow, using over a stochastic variable. So there's no way to backpropagate. If we're sampling from something, how do we differentiate that? So that was the real, the stopping thing, that even though deep learning was progressing in other fields, we couldn't apply VI, variational inference, because we couldn't backpropagate through a stochastic variable. So the thing that changed all that, and that was with Kingma's paper, and it's also used in other areas of maths as well. It's got different names. It's called reparameterization trick in VAEs. This is actually to sort of reformulate how you're calculating the parameters of the distribution. So I'm going to go through it now. So we need to sample from this posterior distribution that we're learning here. We encode an image, we get a vector out, but we need to add some noise to that and sort of compare it against our prior, but we can't backpropagate through a stochastic variable in order to achieve a sample to then decode it. Right? So how do we actually backpropagate through this? So the idea is that we actually encode the parameters of our distribution. In this case, the mu and the variance, this was standard deviation, doesn't matter, squared, of a Gaussian. So let's pretend we're just dealing with Gaussians for now. What we're going to do is we're going to give the network a vector to encode. It doesn't know that it's encoding the parameters of the distribution. It's dumb. But we're going to say, well, this part of the vector is mu, this part of the vector is sigma, and that's going to be the parameters of our Gaussian. So then we need to achieve some kind of sample from a Gaussian. So the idea is that we sample from our prior, which is a noise source, and this is external to the network. So this is a bit like another data input, essentially. We stick a sample in that comes out of our prior distribution. So just for the sake of argument, we're going to make that a mean zero covariance, diagonal covariance, just keep it really simple, Gaussian. Pick that sample out, and then we're going to multiply it by our variance and add to it our mean. So it might seem like such a trivial thing to do, but this was literally the thing that was gating our ability to apply VI in deep learning. So now when we backpropagate, we're only backpropagating through these simple functions, multiplication and an addition, which is fine. What we're doing is we're injecting noise here and then basically reparameterizing this noise given the parameters that we're learning. That kind of makes sense? ish. Yeah.
Are there equivalent tricks for if we don't want to use a Gaussian in the middle?
Yeah, you would have to just learn. You'd have to learn. Yeah, I guess you'd have to know. You'd have to be able to sample from the distribution to begin with, and then you'd have to be able to reparameterize it effectively. So I mean, I guess you're limited to whatever distributions you could use for that. Other people use. Actually, no, even then. So if you were using a flow-based model, you would still sample from noise, but then you'd apply a lot more transformations to get to where you want to go. So there's nothing stopping you from turning this into something bonkers. Start with Gaussian and then end up with some crazy nonlinear distribution.
Can I ask the same question in a slightly different way? So out of the 300, has anybody else ever done it non-Gaussian?
Don't think, not straightforward reparameterization like this. There's people that have used hyperspherical latent spaces, and I haven't looked at the details. Yeah, I imagine it just, yeah, you just need to adapt it for whatever you're doing, and if there is a way, I'm not sure. So. Yeah, the most common one I see is flow-based. So if you want to get this into something crazy, you can actually learn that distribution, and then you apply lots of transformations to it. But not necessarily saying the parameters that this learns are this, and I can just apply straightforward operations. I mean, essentially the same thing, but you can concatenate lots of operations in order to shift your distribution to something whatever you want. All right, so this is the maths for why we need it. I don't imagine this is particularly interesting to anyone. I don't know, but just very briefly, we're trying to, this is where it all comes from. We're trying to calculate the gradient with respect to some parameters phi. This is our inference. So there's a nabla here to represent the gradient. But the trouble is that the expectation that we're taking actually contains that same parameter in it. So again, up till now, we didn't have a way. There are different maths ways to do it, but in deep learning, we didn't have a way until 2014-ish to actually optimize over something that had an expectation where the parameter was in the expectation that you're trying to take the gradient of. So this is just reformulating it. We have some other function g, which we can backpropagate through, and then we just apply that instead. So we end up by taking the expectation on the outside, because our nabla is no longer related to that particular parameter, epsilon, which is our external noise source. Now we can take the expectation over the gradient itself. So here's the noise sample. We're applying a function g, which is shifting it by the variance, moving it according to the mean, and then we apply our actual function that we're trying to learn, and that's where you end up. Also known as pathwise derivative. So other people who've done maths degrees may have come across stuff like this before. So now I can return to this and actually embellish it. So this is actually how you would probably see it in full online if you're looking for a VAE architecture. So things are kind of similar, except now I've got this mean and this covariance that I'm learning. I'm injecting some noise, epsilon, which I'm sampling from a normal distribution. This I here is no covariance, it's just diagonal. And this is the prior, P of Z. I'm going to choose approximating distribution Q phi of Z given X, our posterior distribution. And that's parameterized by what we're learning by our network. So I'm going to go through the full training procedure so it's really explicit, and hopefully you can even implement this yourself in code. So one of the reasons why we always choose mean zero identity covariance Gaussian is because it's simple. But it also gives you an advantage, which is that all of your latents become independent of each other. So if you're pushing your posterior distribution to look like the prior, then you're essentially making each of those latent factors independent of one another because they become more and more diagonal. And in fact, this is a vector. This isn't a matrix. If you wanted to get a bit more fancy, you can make this a covariance matrix, and you can start to learn the full set of covariance parameters. And that would make your learned distribution a bit more flexible. You'd be able to learn correlations between latent factors. But I guess this is just what's been used because it's straightforward, and also you get that independence between the dimensions. This is just stating the independence thing. If you want to look at the sort of joint over all of the factors, you just take the product of those individual factors. They're all independent of each other, so it just makes everything sort of straightforward. And here's our reparameterization trick, injecting the noise. In terms of choosing the dimensionality of these, this is really up to you. I would suggest using a bit of domain knowledge It's quite difficult, because if someone said to you, how many latent factors do you need to represent a face, what would you guess?
20.
20? Alright, so there's ballpark. I have no idea if that's right or not. Give it a go. See how many are empty by the end of it. So when you actually visualize the latent space, like using those traversals, you can see if any of them are actually doing anything. If you tweak them and they just stay the same and the image doesn't change, then you know that that's not a useful latent factor. That doesn't mean that it couldn't be useful, but it just means that you've pushed it so much to be like the prior, it's killed it. It's a bit like doing PCA in a non-linear way, right? Or probabilistic PCA. Okay. So this is the training procedure then. And I think this will take us up to the hour. Oh, sorry about that, it's broken. Oh, it's gone off.
No, don't worry.
Sorry.
It's good.
Oh, was it right? Oh.
I'm recording from the backup.
Okay. All right, so this is the training procedure. So if you wanted to go away after this and implement your code, this is what you would do. You need to be able to sample a batch of images. I assume you probably figure out how to do that. You're going to encode this into that vector that your network doesn't know, but you're saying this half is mean, this half is the diagonal covariance. It's just a vector, but you know it's what it's going to be used for. Then we're going to inject a bit of noise from a noise sample. So we're going to take that epsilon, we're going to pass it in, and then we're going to basically process that noise according to the reparameterization trick by multiplying it by one half of the latent space, and then adding to it the other half of the latent space. So this is what makes it learn the mean and the covariance. It doesn't know a priori, it's just a dumb network. But after you do this, it sort of forces it to behave in that way. Once I've got this noise sample, which is the reparameterized noise sample, then I pass it to my decoder, straightforward. Transpose convolution, make it deep, whatever you want to do, and then try and reconstruct the input. So then you're going to apply a loss function, which compares your reconstruction against your original image. If it's like binarized MNIST, you can just use cross entropy, binary cross entropy. If it's real valued 3-channel color image, you can use mean squared error, or you can use whatever loss you want to chuck in. Yeah, that's what I did for my lol. So then at that point you've got your reconstruction loss, which is actually your conditional likelihood, that term in your objective function. That's literally what you substitute in. That's your mean squared error loss in there. And then for the KL loss, you can do this analytically by writing this out. It might look horrendous, it's not actually that bad, but this is if you go online and you find the code, they're all sort of variations on a theme. Variation on the theme, not intentional pun. But you can see, you can actually tie this up to this equation fairly straightforwardly. So go online, find the KL equation. Essentially, it's just taking the different halves of the latent vector that you've learned, saying, well, this one's my variance, I'm going to apply a log to it. That's essentially to make a standard deviation, and so on. If you haven't already squared it, it doesn't really matter. Your network doesn't really know whether it's squared or not, it's just learning a value. So it's however you treat it. And then this here was that mean squared error here. So you can apply this fairly straightforwardly, and you can do this for a batch. So you're sort of doing this stochastic gradient descent, and you're calculating KL analytically, but only if you're in that Gaussian mean zero sort of way. If you don't want to do this and you want to do something fancy, you can actually sample it. You can calculate the KL using samples. TensorFlow, it's a great deep learning library, but it's also got an example online about how to calculate KL using samples. So you can do that Monte Carlo style if you want. And then you can sample from the latent space, calculate your KL. It's like a sample-based KL. And it's a little bit more noisy because it's sample-based. Monte Carlo, in the limit, tends towards a perfect approximation, but obviously if you're using small samples, it's probably going to be a little bit more noisy. But otherwise, use its analytical form. And then you compute these two losses, backpropagate, and then repeat until you're done. You follow the loss, it will converge. You won't see that kind of divergence that you get when something overfits. Because again, you're in Bayesian territory here. You're unlikely to overfit. Depends on what that value of the beta is. If you make it autoencode more, you'll get more overfitting. But if you're doing sort of a vanilla VAE version, then you'll probably avoid overfitting. So very, very finally, I'll just get this stuff out of the way, and we'll have a break. So I mentioned to you before that we're optimizing a lower bound on the log likelihood. That's the thing we really want to compute. Then we'd be entirely in explicit territory. We'd be able to compute exactly how well our model's doing. We're actually using this proxy because we don't know our variational distribution, so we've approximated it. So we end up with this lower bound. This could be your lower bound here, this blue curve. and we want to push this as high as we can to try and approximate our true log likelihood. There are two sources of error. The first one I've already told you about. This is this approximation gap. The fact is, if we pick a variational distribution that's nothing like our true distribution, then we're never going to approximate it very well. But the other issue is we're amortizing over all possible values. Now this should be easy to squeeze if your encode is powerful enough. So there's actually no disadvantage that I'm aware of to using a really powerful encoder. There are actually disadvantages to using a really powerful decoder. So if you want to sort of give your network the most opportunity of encoding information, have a nice deep convolutional network for the encoder, and we'll talk after the break about the decoder. But doing that will help remove this amortization gap because your network is perfectly powerful enough to encode as much as it can. As much as it can. Now, very briefly, the last thing is for RL people and semi-supervised learning. If you want to inject supervision, you can. It's actually quite straightforward. Take our original image. This is going upwards now. Take our original image, encode a latent space, but also try and predict a label Y, as you would normally with, say, a classification task. You compare this when you're training against the true label, here, and then what your network learns to do is not only encode this latent space here, but also to predict a label for you. So if you're training this on MNIST, then it will predict, say, the digit class, but also encode all the other stuff in here. It will encode style, thickness of the digit, whatever other MNIST latent variables you can think of in here. But because of information bottleneck theory, it's not, so long as your network isn't like too overly powerful in terms of how much it can put in here, and if you're using this variational inference, it should try and penalize it anyway, then this will only contain that information. It shouldn't be correlated with your class label. All your class label stuff is here. So that when you come to test time, you don't need your class label, but you can specify if you want. So that basically means that this is completely invariant to your class label. And then your decode is the same as before. And these PGMs just sort of correspond with that, various ways to organize your network. Finally, for RL people, you might be thinking about sequences, or even NLP people. I don't know how many NLP people we have here. NLP. So if you want to build this into a recurrent neural network, you have your image here. You end up predicting this hidden state here, but you're also inferring the latent variables through your previous hidden state. So now it's quite nice because your current latent variables are influenced by both your input image and your previous hidden state. So this hidden state becomes the state that you'll be using for your RL agent, I assume. And then for generation, it's like the other way around. You use the current latent space, but also the previous hidden state. So in other words, everything about this becomes recurrent. Your latent space depends on the history, and so does your current hidden state, obviously, as usual with RNNs. Any questions about any of this stuff?
About the previous line, basically, when you add the classification task, you just make one part of the latent space explicit and the other one stay implicit. And
Yeah.
because of the loss, they become independent.
Yeah, exactly.
But, yeah.
Yeah, and again, the advantage is you don't need the labels during test time at that point if you don't need them. I mean, it doesn't have to be for MNIST, whatever you want. But, yeah. All right. We'll have a break then. Should we say 15 minutes? 10, 15?
You're in charge.
All right, I'm in charge. Let's go for 12 and a half.